Basically an overview of the different energy that we can use. The sun, solar. So there are different possibilities of feeling the energy. But for this presentation, I just focus on the turbine, tidal current turbine. So we can have energy as solid waste, but the only problem is that in Malaysia the wave is small, you know? So still have to do some kind of design how to capture the. Also from my presentation, I'll focus more on the tidal current. Offshore wind, so there is already a well established offshore wind. So thermal energy, you know. Tidal range.
Recording in progress.
Osmotic pressure. Different marine biomass. Using the seaweed and so on. A lot of alternative. But if we keep on increasing, 2020, the big chunk is from the using the tidal current. So that is the tidal shift. So there is a big potential with the tidal. Just this to show that not only connected to India. And the wave and the tidal current. So there's some effect as well. But you can see that the main interest is more with the tidal current. Okay. So this is from the Philippines. Also using tidal current. So you can see that say for the example of the wave pattern, you have so it means that if we can have a device that can oscillate, then we can tap in the energy. This is the classification of wave devices. And waves point global. Oscillating. Yeah? This is the various OWSP submerged, floating. So there's a lot of these devices. Okay. This is one of them. Using the flap. Wave roller. Okay. Next one. Another side, Langley side. Okay. Oh, I see. Yeah. Okay, so this is showing you the schematic of how the energy can be tapped from the wave. Yeah? So you have a different devices, but you can see at the end of the device is some sort of a turbine, yeah, either an air turbine or hydraulic or sort of can be a current turbine. And then where the energy is trapped, and then it can be sent to another, or it can be used locally. Okay, next. So this is another thing about give you indication of how much energy can you tap from the devices. And this is a plot of say the coefficient CP against the speed ratio. That is the ratio between the speed of the rotating blade and the speed of the current. Okay. So in our case, we are in this region, where the current speed is low. So it's very difficult for us to go to the higher speed region, which you can see mainly for higher speed, the propeller type. This is basically what our turbine would look like. It's very similar to the 7S turbine, but it's some different. I will discuss why we have this difference of this turbine blade as compared to the sub-unit. Okay. From the hydrokinetic turbine. So there are basically two types, the axial flow and the cross flow. So the axial flow is basically for the horizontal axis turbine, using the propeller. And for our case, for the low speed one, usually using the vertical axis current turbine or the cross flow type. So you can see all this. So we have this areas, edge area. Okay. So this is the horizontal one, which we are not focusing today because they're mostly using propellers. This is for more for higher speed, of the higher current speed. Next. So this is just a comparison between vertical and horizontal axis current turbine. It seems that the vertical one is much easier to implement and much cheaper than the horizontal current turbine. Okay. The one is actually to put your turbine somewhere just below the surface, Just looking at the velocity profile. So almost maximum the profile is near the surface of the sea level. So we need to have sort of floating turbine. It is this comparison of the one that we are proposing, this type of turbine.